All right, next we're talking about the Limacon curve. So we're going to take a look at Limacon curves where a is greater than 0 and b is greater than 0. So a is now shifted out here. It's being added or subtracted to b times the sine of theta or b times the cosine of theta. So a is now the thing out front being added or subtracted. B is now the value being multiplied by the sine or the cosine. And depending upon the relationship between these a and b values determines which type of a curve we get. So there's 4 types. The first one is called convex. And a convex curve, it's almost like flat on one side and then curved around. And this is going to happen anytime the a divided by b is bigger than or equal to 2. So if we take the number being added and divide it by the number being multiplied by the sine or the cosine, if we get something bigger than or equal to 2, it's going to create this shape called a convex Limacon. The next type we can get is called dimpled. And this is going to occur if the a divided by b is between 1 and 2. And it's got this little dimple in the side of it. The third case is called a cardioid. That little dip in the side is even deeper and it looks like a heart shape. And this occurs in the very specific case where the a divided by b equals 1. So if it equals exactly 1, it's called a cardioid. It looks like a heart shape. All right, if a divided by b is less than 1, we get our final type, which is called inner loop. And on an inner loop graph, you see it curves in on itself, and we have this little loop on the inside. So those are the 4 types, and again, to determine which type you're going to get, you take the a divided by the b. Bigger than or equal to 2, it's convex, it's almost flat on the side. Between 1 and 2, it's dimpled, so a little dip in. If it exactly equals 1, deep, so it looks like a heart. And if it's less than 1, it's going to go in and loop inside of itself. Symmetry rules still apply, so if it's sine of theta, we know it's going to be symmetrical about the y-axis. If it's cosine of theta, then we know it's symmetrical about the x-axis. To figure out the important points to plot, we will always go by pi force. So for the rose curves, we had to take pi divided by 2 times n to figure out what to scale our table by. But for Limacon curves, where you've got a number out front being added or subtracted to the sine or cosine, you're always using pi force. And to help us with graphing, we're going to use some approximations for the sine of pi force and the cosine of pi force. So generally we talk about them as the square root of 2 divided by 2, the rationalized exact answer. But if we're going to graph, we need to know what does that mean? Where should we put it on our grid? So square root of 2 divided by 2 is approximately 0.7, and that's what we're going to use to estimate the value of sine of pi force and cosine of pi force. All right, so in this first example, a is 4, b is 2. So a divided by b, 4 divided by 2, gives us 2. So remember, if we equal to or are bigger than it, we're going to get a convex graph. So it should look like this, almost flat on one side and then curved around. Because it is cosine, we know it will have x-axis symmetry. All right, so again, we always start at 0, and we're going to count by pi force. So 0, pi over 4. Next would be 2 pi over 4, but that would reduce to just pi over 2. And then we have 3 pi over 4. And then we would have 4 pi over 4, but that will reduce to just pi. And then we have 5 pi over 4. 6 pi over 4, but that would reduce to 3 pi over 2. 7 pi over 4. And again, that one's not going to reduce at all. And then 8 pi over 4, which would reduce to 2 pi. All right, so now that we have our table scaled, I'm going to go ahead and remind myself where pi force is here on these grids. Remember, this would be pi fourths. This would be 3 pi over 4. This would be 5 pi over 4. And this will be 7 pi over 4, since we're going to be plotting values. Let me just go ahead and mark those off on my grid to make it a little easier. All right, now one at a time, we'll take theta, plug them into the equation. So if theta is 0, we have 4 minus 2 times the cosine of 0. Well, we know the cosine of 0 is 1, so 4 minus 2 gives us 2. If we plug in pi fourths, so 4 minus 2 times the cosine of pi fourths. And again, we're going to estimate the cosine of pi fourths as 0.7. So 4 minus 2 times 0.7. Well, 2 times 0.7 would be 1.4. 2 times 7 is 14, 1 decimal place, so 1.4. So 4 take away 1 is 3, and then 3 take away 0.4 would be 2.6. All right, next one. So 4 minus 2 times the cosine of pi over 2. Well, we know the cosine at pi over 2 is 0. So this one's just going to end up being 4, because 2 times 0 would be 0. So 4 minus 0 just gives us 4. All right, so if we plug in 3 pi over 4, so again, we're going to estimate as 0.7, but because we're over in quadrant 2, it's negative 0.7. So it'll end up being 4 plus the 1.4. And so we're going to get 5.4. All right, next one, 4 minus 2 times the cosine of pi. Well, we know the cosine of pi is negative 1. So this becomes 4 plus 2, and we're going to get 6. All right, if we plug in 5 pi over 4, that's down in quadrant 3, so we know the cosine is negative, and we estimate the cosine of pi fourths is 0.7, so negative 0.7 times the negative 2 will give us positive 1.4. And so again, we will get 5.4. All right, so if this time we plug in 3 pi over 2, we know that the cosine at 3 pi over 2 is 0. So 2 times 0 is 0, 4 minus 0 gives us 4. All right, so 7 pi over 4, cosine's going to be positive over there, so it'll be positive 0.7, so we'll have 4 minus the 1.4 again. So again, 4 take away 1 is 3, 3 take away 0.4 gives us 2.6 again. And last one here, if we plug in 2 pi, we know the cosine of 2 pi is the same as the cosine of 0, which is 1. Oops. So we've got 4 minus 2, which will give us 2. And so again, we can see the pattern. It went 2, 2.6, 4, 5.46, and then we repeat going the other direction. There's like symmetry to the table. 5.4, 4, 2.6, back to 2. All right, so 0, we're out at 2. At pi fourths, we are at 2.6. At pi over 2, we're at 4. At 3 pi over 4, we're at 5.4. At pi, we're out at 6. Oops. No, I did not send this one quite far enough. Let's see, 1, 2, 3, 4. This one I need out here, sorry. And then this one's all the way at 6. And then we go back, so at 5 pi over 4, we're back at the 5.4. 3 pi over 2, we're at 4 again. And then 2.6 at 7 pi over 4. And so here's that side that's almost straight across. And then it curves out. Oops. Let me just fix up a little bit in here a little bit. There we go. So there's our first Limacon curve. It's convex. It's symmetrical about the x-axis. All right, let's try the next one. So this one, r equals 5 plus 6 sine of theta. So again, I know it's not a rose curve because of this number being added or subtracted out here. So then I know it's a Limacon, and I'm comparing this to this, setting up the ratio a divided by b. So I get 5 divided by 6, which is less than 1. So remember, anytime it's less than 1, you're going to have an inner loop. So it's going to curve in on itself like this. All right, so the type of graph is an inner loop. Type of symmetry, well, because this one has sine of theta, we know it has y-axis symmetry. And we always go by pi fourths. So start at 0, count up by pi fourths. So pi over 4, then 2 pi over 4, which reduces to pi over 2. 3 pi over 4. It's not going to reduce, so I can leave it in the middle. 4 pi over 4, which is going to reduce to just pi. 5 pi over 4, which won't reduce. 6 pi over 4, which reduces to 3 pi over 2. 7 pi over 4, which again won't reduce. And then 8 pi over 4, which equals 2 pi. And again, I'm going to go ahead and remind myself where pi fourths is on our grid here. So this is pi over 4. So this will be 3 pi over 4. Down here we have 5 pi over 4. And over here we have 7 pi over 4 for when I'm plotting my points. All right, now I'm going to take each theta, plug them in one at a time, see what I get. So 5 plus 6 times the sine of 0. We know the sine of 0 is 0, so it's really just 5 plus 0, or 5. If we plug in pi fourths, so again, we're going to approximate the sine of pi fourths as 0.7. So we've got, so 6 times 7 would be 42, with 1 decimal place, 4.2. So we get 9.2. All right, next we're plugging in pi over 2, so we know the sine of pi over 2 is 1. And so then 5 plus 6 gives us 11. All right, if we plug in 3 pi over 4, sine is still positive in quadrant 2, and we will approximate the sine of pi fourths is 0.7. So again, 6 times 7 is 42, with 1 decimal place is 4.2. 5 plus 4.2 gives us 9.2. If we plug in pi, we know the sine of pi is 0 again. So it's really just 5 plus 0, or 5. And so we're seeing that repetition, the pattern in our values here. Next, we're plugging in 5 pi over 4. So now we're down in quadrant 3, so now the sign will be negative. So it'd be negative 0.7, we'll approximate it as. So 5 minus 4.2 this time gives us 0.8. Because 5 minus 4 is 1. 1 minus the 0.2 gives you 0.8. All right, if we plug in 3 pi over 2, we know the sine of 3 pi over 2 is negative 1. So we've got 6 times negative 1. So we're going to have 5 minus 6, and we're going to get negative 1. All right, if we plug in 7 pi over 4, we're in quadrant 4, so the sign is negative there. So we'll approximate as negative 0.7. So we will have 5 minus 4.2 again. So again, 5 minus 4 is 1. 1 minus the 0.2 gives us 0.8. Last one here, so if we plug in 2 pi, that's the same as 0, and we know the sine of 0 or the sine of 2 pi is 0. So it's really just 5 plus 0, or 5. All right, so now that we have our table filled in, we'll plot our points. So at 0, we're supposed to be out at 5. So notice that they're counting by 2. So this is 2, 4, 6, 8, 10, 12, to make sure everything can fit. So 5 is going to be right here between the 4 and the 6. Next one at pi 4, so I got to be out at 9.2. So right around there, we'll say. And then at pi over 2, we're out at 11. At 3 pi over 4, we're back to that 9.2. Then at pi, we're over at 5 again. At 5 pi over 4, we're only at 0.8. So, in about there. At 3 pi over 2, we're at -1. So rather than going out half a block or half a circle this way, I gotta add pi to it or send it through the origin over there. So there's -1 for 3 pi over 2. And then at 7 pi over 4, we're again at 0.8. And then at 2 pi, we're back at the 5. Okay, so we're starting here, we're curving out. Oops. Through these points. Here, into here. So there's my inner loop. And there's my Limacon curve. Again, it's an inner loop because a divided by b, so the number out front being added or subtracted is a, b is the one being multiplied by it, so a divided by b, if it's less than 1, it's always going to give you this inner loop shape that curves in upon itself. Because it's sine, we know it's y-axis symmetry. So there's 2 examples of these Limacon curves that we could get.